Well, I'd like to thank the organizers for absorbing this normal HAO colloquium into the workshop. I hope, the participants here will be interested in what I'm talking about because it's related to dynamos. So I'm really excited to share with you these surprising results that we've published earlier this year. This is work that I did in collaboration with Ricky Egeland, a graduate student here at HAO, finishing his PhD now, and Jennifer Van Saters, a postdoctoral fellow at the Carnegie Observatories in Pasadena. I'm going to give you the punchline up front. We've discovered a fundamental shift in the rotation and magnetism of stars in middle age, in their middle age phase. And the sun appears to be currently in this transition. The transition is occurring right now. Now, this doesn't mean that we can't understand or predict the solar dynamo. It just means that we need to recognize that the solar activity cycle might be a special case of a more general stellar dynamo theory that can explain the cycles that we observe in other stars. And we have to be careful, as a result, about transferring knowledge from one domain to the other. The properties of the sun, in particular, its 11-year cycle, may not be transferable or comparable to the cycles that we're seeing in younger stars. But one of the cool implications is that we actually have a front row seat to characterize the nature of this transition because the star in front of us is doing it right now. So I'm going to start with an overview of the Nature paper led by Jennifer Van Saters in January, describing this rotational transition that we discovered from observations of stars observed by the Kepler satellite. I'll give just a little bit of, say a few words about the source of those observations, and then I'll go into the new work on the magnetic counterpart to this rotational transition. And the scenario that we've developed for the a new scenario for magnetic evolution of stars beyond middle age. So since this is a more general audience than I usually talk to in terms of like astronomers, let me just give you a little bit of background on the Kepler satellite. The Kepler Space Telescope was launched in 2009, and it spent 4 years staring at 100 square degrees of the summer Milky Way, carefully monitoring the brightness of a couple 100,000 stars every 30 minutes for this 4-year period. And the main purpose of the mission was to find Earth-sized planets in the habitable zone of their stars. So you had to have exquisite photometric precision to be able to see some of those stars that they're monitoring are going to have planets, and some of those planets will be oriented just right that they'll pass in front of their star, and you'll see a tiny dip in the brightness, a transit. And to measure the transit of an Earth-like planet around a Sun-like star, you need parts per million photometric precision. But by design, just with geometric probabilities, only a few % of those couple 100,000 stars were going to show Earth-sized planets. And so the other 95+% of the targets were fantastic data sets for stellar astrophysics. And those are the data sets that we're drawing on for this study. So this story really begins here at HAO more than 40 years ago with Andy Skumanich, a longtime scientist here. In 1972, Andy noticed from observations of a couple of young clusters and the sun that the rotation rates tended to decrease over time, and right in step, the activity, some proxy of the magnetic activity, in this case the calcium H and K emission, also decreases, and you can describe those decreases with a power law that's basically both of those things decreasing with the square root of the age. Now fast forward a few decades, but before the Kepler mission, and the story gets a little bit more complicated. So stars are born with a range of initial rotation rates. So we're looking at rotational frequency relative to the sun versus age, both on a log scale. So stars are born with a range of rotation rates. They spend a short period of time locked to their protostellar disks. They then contract onto the main sequence and spin up a little bit. And then they begin the slow decay caused by magnetic braking due to their magnetized stellar winds. And somewhere around 1 gigayear or so, those, despite whatever the initial conditions were, those initial conditions are forgotten and the stars obey the Skumanich relation, right? They just spin down over time, t to the minus 1/2. Now, this is before Kepler, so the oldest cluster that we had was somewhere around 500 million years. And then beyond that, the only other calibrator we had for these observations is that of the sun. We know the age of the sun because we can date the meteorites, right? And it turns out if you do modeling of the helioseismic observations, you can derive an age for the sun that agrees with the meteoritic values. But prior to Kepler, this relation at old ages beyond 1/2 or 1 gigayear relied entirely on the sun as the old age calibrator. Okay, so Kepler, the first thing that Kepler did to change this story was to observe a couple of clusters that happened to fall in the Kepler field that were older than the ones that we'd had previously to calibrate this relation. It's just an empirical relation. There's, as we know now, physics behind it, but people treat it as an empirical relation just to be fitted. So if you can identify the ages of a certain star or population of stars, and you can measure their rotation periods, you can calibrate this empirical relationship. So it helps to finally get from Kepler 2 clusters, one with an age around 1 gigayear, and another with an age around 2.5 gigayears. So this is now not just an empirical relation, but detailed rotational evolution models, isochrone, that passes through all those clusters, and there's the sun there. So now we're looking at period instead of frequency versus age. So the first thing Kepler did was provided 2 new data points for this empirical calibration. And by and large, those new data points from those clusters at 1 and 2.5 gigayears agreed with what we knew before. But the next thing that Kepler did was it allowed us to derive ages for individual field stars from asteroseismology. And when we add those points to the picture, so these are stars where we have asteroseismology to provide the age, and we can measure the rotation period just from spot modulations. Then it looks like this. So it's not quite as clean. And the main thing that you notice is that, by and large, most of the points fall below the theoretical expectations. That is to say that stars beyond the age of the sun or so tend to be rotating more quickly than you'd expect if the Skumanich relation continued indefinitely beyond the age of the sun. So we set out in Van Seters et al. In the Nature paper to explain this. Now it looks pretty bad, but part of that is because we're showing stars of a full range of temperatures and so spectral types or masses, right? We're not just including G-type stars like the sun here, we're also including hotter F-type stars and cooler G-type stars. So part of the scatter might be due to the fact that we're lumping all of these stars in together. And those different types of stars actually have different expectations from magnetized magnetic braking. So they spin down at different rates at different parts of their lives. So if you look at the predictions, this is the G-type stars. This flatter one is for K-type stars, and this steeper one here is F-type stars, right? Here, as the period gets longer, here, this is where the star is becoming a subgiant. And so it's changing its moment of inertia as it's expanding. So to do a proper analysis of these data, you need to compare the F stars with the F isochrones, the G stars with the G isochrones, and so on. Okay, so let's do that. Here are the F-type stars, the hotter part of our sample. And so compared to their isochrone. And what you see is that up to, around 2.5 gigayears, there's relatively good agreement between the asteroseismic ages and rotation periods But beyond that, there starts to be these deviations. For the G-type stars, it seems to hold until somewhere around the age of the sun, and it's beyond that. So beyond somewhere around 4 gigayears, that you begin to see the systematically faster rotation periods for the G-type stars. And for the K-type stars, there are relatively few of those in our sample because the solar-like oscillations are much more difficult to detect in those cool stars. The amplitudes are very low. But you see those tend to agree out to longer, to ages of somewhere around 6 or 7 gigayears. Okay. So this dependence on spectral type, the fact that the deviations that we're seeing kicks in earlier in absolute age for the hotter stars and later in absolute age for the cooler stars, suggests a connection to the Rossby number. So the Rossby number is the ratio of the rotation period to the convective turnover time. And since cooler stars have deeper convection zones, they have longer convective turnover times. And so we posited in the Van Saters paper that maybe you could explain this as a Rossby threshold of some sort. So here are a few modified predictions where you, at some critical value of the Rossby number, you turn off magnetic braking. You say, magnetic braking operates as normal, as we always thought it did, up until a certain Rossby number, and then it stops. And the bottom curve here is for a Rossby number of 1, so normal evolution, and then you start to get a deviation. You basically stop braking. You lock in your rotation period at that rate because you've stopped slowing it down until you get to the subgiant phase. This is for a Rossby number of 2, and this is for a Rossby number of 3. And so we could fit for the best value of this single parameter, the critical Rossby number, that could explain all of these observations of a sample of 20-some Kepler stars. And it turns out the best value was around 2. A Rossby number of 2.1 would explain all of these data best. So let me show you that in greater detail, again, separating out by the 3 different types of stars. So here's the prediction with that modified model for the F-type stars, the hotter stars. And the gray shaded area here represents the full range of temperatures and metallicities in the grid of rotational evolution models that encompasses the same range of temperatures that's in the sample, right? We have to bend them up by temperature somehow, and so there's going to be a natural range in the predictions depending on that temperature, because it's a proxy for the mass of the star, right? So you can see we can explain reasonably well the deviations that we see in the F-type star with that Rossby threshold fixed at 2.1. Oh, sorry, and just to note, you see there that the deviation, the break in the curve kind of happens around 2.1, where 2 or 2.5 gigayears for the F-type stars, like we saw. Here's for the G-type stars. And here I want to draw your attention to the position of the sun in this diagram. It's beyond the best value for the break. That's the Rossby, critical Rossby number 2.1, and it varies a little bit with temperature, but the sun is clearly beyond that critical Rossby number where we believe magnetic braking shuts off in solar type stars. And here for the cooler type stars, again, we reproduce the break at the larger absolute age to explain those cool K-type stars. Okay, so those are the observations that motivated a follow-up study to try to characterize the magnetic counterpart to this rotational transition. As we know, rotation and magnetism are intimately linked, and so if there's this transition in the rotational behavior of stars beyond middle age, then what could be the magnetic cause, the underlying magnetic cause of that loss of magnetic braking? And in the Van Saters paper, we basically said, one way to do it is you get rid of the largest scale components of the magnetic field that are responsible for most of the angular momentum loss. I'll come back to that a little bit later. But first, let me just say a few words about the nature of these observations, where these observations come from, to sort of assuage any doubts that this observation might be caused by a conspiracy of systematic errors. So this image really represents the other two signals that are in the Kepler data that we're using to characterize these stars. Of course, the sunspots or the star spots, you know, typical size, like even as small as the Earth on the sun. And since Kepler was designed to detect the shadows of Earth-sized planets as they pass in front of their stars, it's also sensitive to those passage of star spots. And you can see the variations quite easily due to the rotational modulation as these star spots go into and out of view. And the other source of signal here is the granulation pattern. The granulation, the overturn of these granulation cells creates acoustic noise at essentially all frequencies. And some of those frequencies are resonant inside the spherical cavity of the star and set up standing waves, standing sound waves, that create global oscillations that result in tiny variations in the brightness of the star that we call solar-like oscillations. You can still see it in disk-integrated observations. So here's one example of how we measure a rotation period for a Kepler target. So we're looking at flux in parts per million. So the full scale here is plus or minus 0.1%, a millimagnitude, over close to the 4-year duration of the Kepler mission in this case. And you can see these clear variations in brightness caused by the passage of star spots onto and off of the star. You know, this is well below the variation that you can easily observe from the ground, let alone continuously for 4 years. So these are exquisite data for measuring the rotation periods of stars. And what I'd like to say about the quality of the rotation periods that we derive from the Kepler stars is just to say that this paper Garcia et al. Basically takes two different sets of light curves, the standard data products from the Kepler science team, and then a custom set that are optimized for asteroseismology, really, to remove, in a better way, the remaining systematic uncertainties due to the quarterly rolls of the spacecraft that are marked here in dashed lines. Every 3 months, the spacecraft had to rotate 90 degrees to keep the solar panels pointed at the sun, keep it powered up. And this resulted in the stars moving from one detector to a different detector in the instrument, and so you have to compensate for those systematics. Garcia et al. Had this methodology where they take two sources of light curves, they pump it through two different types of analysis, and only when all 4 of those independent analyses resulted in the same rotation period would they call it a detection. So these are the best of the best. They are the most reliable method of retrieving rotation periods from Kepler data. For asteroseismology, so this is a sample power spectrum of a Kepler star. This particular one happens to be 16 Sig A, a well-known old version of the sun, an old solar analog. And if I showed this to you 30 years ago, you would have thought this was the original detection of solar-like oscillations in the sun. This is like a disk-integrated signature of solar-like oscillations. And there's a couple of levels of analysis that you can do to characterize the solar-like oscillations, relying on either just these global properties. So basically what you see is a series of, a comb-like pattern, a series of regularly spaced peaks. The spacing is the frequency, sorry, it's called the large frequency separation. And it's basically the frequency separation between modes with the same angular degree, so radial modes with consecutive radial overtones, okay? But it's not just the radial modes, there's dipole, quadrupole, octupole modes in there as well. But they all have this same regular frequency spacing. And that frequency spacing reflects the mean density of the star, basically. The other global parameter that you can define is the sort of peak in power in this power spectrum, the frequency of maximum power, nu max. And that basically scales with the surface gravity and effective temperature of the star. And so you can combine these two things, one that reflects the mean density, one reflects the surface gravity, and you can, even without any stellar models, derive the masses and the radii just from simple scaling relations from the solar values, if you've got also an effective temperature. So that's been done for hundreds of stars in the Kepler field. As soon as you add models to the equation, you can get a bit more precise values for those and also get ages at some level, maybe to 20% precision. But our analysis was restricted to those stars, the highest signal-to-noise stars, where not only could we detect this regular spacing and the frequency of maximum power, but we could extract the individual oscillation frequencies for dozens of oscillation modes and model those in detail. So again, the asteroseismic data and the asteroseismic ages are derived from the best of the Kepler data. That's why our sample only includes a couple dozen stars. So when you take a data set, a Kepler-like data set for the sun, and pass it through our method, we have an automated sort of modeling method that uses a low-level form of artificial intelligence to model each star automatically and uniformly. If you take a Kepler-like data set for the sun and pass it through this modeling pipeline, you retrieve the solar age and all of the other parameters with better than 5% absolute accuracy. As a second test, you could put the individual components of the binary system, 16 sig A and B, and put those data sets through this method. And when you do that, putting those two stars through independently, not only do you get the same age as you expect for the members of a binary system, but you also get the same composition for the two stars. So this gives us confidence that our asteroseismic age scale is not only precise, in fact, the most precise that you can get from these type of data, but also accurate. Okay, so let me step you through the new scenario for magnetic evolution that we think is the counterpart for what's driving this rotational transition in middle-aged stars. So this is a plot of a rotation activity plot. So we're plotting a proxy for the chromospheric activity. This is log r prime hk, so it's based on it's the ratio of the luminosity in the calcium H and K line cores to the bolometric luminosity of the star, so we can compare samples with different luminosities, all on the same scale, versus the rotation period, okay? You got the active stars up here, inactive stars down here, separated by this Vaughan-Preston gap. The Vaughan-Preston gap has been known since the 1980s. I'll come back to that in a little while. Our points, the points from our sample are colored points here. Blue points are the hot F-type stars. These yellow-orange points are the G-type stars like the sun, and then the red points are the cooler K-type stars. We've got the other star points here are G-type stars from the Mount Wilson survey, and so they show a similar sort of, occupy a similar part of the diagram, but provide the context at higher activities where we don't see Kepler targets because very strong magnetic activity actually suppresses the solar-like oscillations, so we can't observe the oscillations in those youngest stars. Okay. And then the connected points from the Mount Wilson survey here connect a series of well-studied, well-characterized solar analogs. And so I'll come back to those later as well. Okay, so we think that the story actually begins not at a Rossby number of 2, but at a Rossby number of 1. At a Rossby number of 1, a large array of simulations suggest that there may be a sudden transition, a transition in the character or nature of differential rotation. The simulation suggests that that transition is such that At lower Rossby numbers, you have a solar-like differential rotation with a fast equator and slow poles. But as you move to larger and larger Rossby numbers, so older and older stars rotating more and more slowly, that will transition to anti-solar differential rotation, where it's the poles that are spinning faster than the equator. I mean, the fundamental argument for this is that a Rossby number of 1 means that the rotation period becomes comparable to the convective overturn timescale. And since differential rotation is an emergent property of convection that's caused by the influence of Coriolis forces on the convection, beyond this Rossby number of 1, the convection sort of stops feeling the Coriolis forces. The rotation period just isn't fast enough to create that differential rotation pattern anymore. Okay, it might not be as simple as a transition from solar-like to anti-solar differential rotation. And there's very little observational data at this point for any stars with anti-solar differential rotations. So we'll just take the simulations at their face value for now. But one of the consequences, we think, of this, the beginning of this transition at, sorry, there's some spilled water back here. Not mine. It can explain this long-standing mystery about the Vaughan-Preston gap. So the Vaughan-Preston gap is basically just the fact that if you take the Mount Wilson sample and do a histogram of the activity levels within that sample, so this is the Mount Wilson calcium H&K survey that ran for several decades and tried to look for solar cycles in other stars, right? And this is what it looks like. It's a bimodal distribution. You have a population of inactive stars and a population of active stars. And here's the gap in between. There are no stars, but relatively few stars between these two populations. And we think that the Rossby number of 1 around here triggers a phase of rapid magnetic evolution that propels stars across the gap. So they just don't spend very much time in that range of activity levels, and they quickly move, triggered by that Rossby 1 threshold, they quickly move across the gap and become inactive stars. There's some evidence for this about observations of clusters of various ages. If you look at stars around the Vaughan-Preston gap, you can pin down the age that this crossing takes place. And in particular, in this 1.2 gigayear cluster, the F-type stars are on the active side of the gap, and a 1.4 gigayear cluster, the F-type stars are already on the other side of the gap. So we know that that transition takes something of the order of 200 million years and happens at an age, for the F-type stars at least, somewhere between 1.2 and 1.4 gigayears. In our sample, the 2 most active stars from the Kepler sample actually span the Vaughan-Preston gap. And we have their asteroseismic ages at 1.1 and 1.7 gigayears. So this is consistent with the results from cluster studies. It's not as precise, obviously, but it also validates the asteroseismic age scale that we have for F-type stars. So we knew already that the asteroseismic age scale for G-type stars was good because of our experiments with the Sun and with 16 sig A and B. And this gives us confidence that the F-type stars are also on the correct age scale. Okay. The other thing that happens across the Vaughan-Preston gap has been known for a while as well. This is a plot of, this is sort of the sense of photometric variation relative to chromospheric activity variation on stellar cycle timescales. So each point in this diagram is a star that has been surveyed for decades for chromospheric variations, like analogous to the solar cycle, and have simultaneously been monitored in photometry to see how their brightness varies at the same time that cycles are going on, right? So we know in the sun, at magnetic maximum, the sun's actually brighter because the sun is dominated. The brightness variations of the sun on cycle timescales are dominated by faculae rather than spots. And the additional brightness due to faculae or plage during magnetic maximum outweighs the negative contribution of the relatively small spots on the sun. But that's not true of all stars. Young active stars turn out to be spot dominated. Their spots are a lot bigger. And so the negative brightness contribution from spots at magnetic maximum actually outweighs the faculae. And it turns out that the transition from spot dominated stars to faculae dominated stars occurs right across the Vaughan-Preston gap. Now, it might be a coincidence. Some authors at Max Planck Institute, MPS, looked at trying to reproduce this feature by looking at the spot area coverage and faculae area coverage of the sun over the solar cycle, and then extrapolating to higher activity levels. What they found was that faculae area coverage basically scales linearly over the solar cycle, while spot area coverage varies quadratically. And so if you extrapolate out to higher activity levels, you're going to eventually get dominated by that quadratic spot dependence, and you become spot dominated instead of faculae dominated. Now, they didn't offer a physical mechanism for why spots should be dominant in younger stars or more active stars, or why that quadratic dependence is in the sun at all. But what we speculate is that this same trigger at a Rossby number of 1 not only propels stars across the Vaughan-Preston gap, it also leads to an accelerated decrease in spot area relative to faculae that the sun is experiencing now. Okay. So, how do we break magnetic braking? After you cross the Vaughan-Preston gap, you run into this Rossby equals 2 threshold where magnetic braking seems to turn off. Here are rotational evolution models from Van Sater's work translated into this activity rotation plane using the activity rotation relation from Mamajek and Hillenbrand, 2008. So you just convert Rossby number into activity using their relation. You have to extrapolate at these very lowest activity levels because they even found that things started going awry at those high Rossby numbers. So what you're seeing here are model tracks for a typical F-like star, G-type star, K-type star. And so you can see that most of the spread in rotation periods is caused by the variation in the convective turnover times of our sample, F, G, and K stars, right? So, and you see that in the G-type stars from the Mount Wilson survey as well. The later G-type stars are over here, and the earlier, hotter ones are over here. Okay, so the Kepler sample is great because we know detailed stellar properties for all of these stars, including their ages, but they're faint stars. We don't have decades of observations of them to know their stellar cycles or maybe even differential rotation characteristics. But the Mount Wilson stars, we do have those observations. And so what we tried to do was use these well-known solar analogs to sort of characterize this transition and develop a story of what's actually going on based on what we know of these very well-studied, well-characterized stars. So let me step you through that in a little bit more detail. So recent simulations of angular momentum loss due to these magnetized stellar winds have revealed that the angular momentum loss depends very sensitively on the topology of the magnetic field, in the sense that most of the angular momentum loss is actually due to the dipole component of the field and smaller and smaller contributions from the higher and higher order, that is smaller and smaller spatial scales fields. So I don't know, it's something like 80% of the angular momentum loss can be attributed to the dipole component alone. And so that's one of the reasons we suggested that a disappearance of the dipole field could be almost enough by itself to explain the absence or dramatic reduction in the efficiency of magnetic braking beyond this threshold. So is there any evidence for that among these solar analogs? Well, two of the solar analogs that we chose have been characterized with Zeeman Doppler imaging. This is a spectropolarimetric technique that can reconstruct the large-scale magnetic field of distant stars, even out to rotation periods of like the solar twin, 18 SCO, at 23 days. So the results of this study by Petit et al. 2008, looking at a sample of solar analogs with various rotation rates, basically recovered two things from the Zeeman Doppler imaging. The first thing is something we already knew, that the mean magnetic field strength, so this is rotation period, is really a proxy for the age, as long as magnetic braking is operating. The mean magnetic field strength decays to weaker and weaker fields in more slowly rotating or older stars. We knew that since the 1970s, thanks Andy Skumanich, right? But here they're actually directly measuring the magnetic field. The other thing is a bit of a surprise, and that is that a larger and larger fraction of the magnetic energy is concentrated into the poloidal component of the field. Now, differential rotation is the mechanism that converts poloidal field back into toroidal field. And so the fact that more and more of the magnetic energy is getting stuck in the poloidal component suggests that differential rotation is becoming less efficient at recycling that field into the toroidal component. So that's, let's say, circumstantial evidence that differential rotation is the thread that connects this whole story. So let's look at it in a little bit more detail at the Zeeman Doppler maps of those two stars. These are the two stars that are closest in age to the sun, not the very youngest ones, but the oldest part of their sample. So a 2.5 gig-year star, HD 76151. This star is dominated by the dipole component. You can see it here in the radial Zeeman Doppler map. By the time you get to 18 SCO, the solar twin, it's just a little bit younger than the sun at 4 gig-years. You can already see that the dipole component is waning, and it's dominated by the quadrupole in this case. And again, here you've got 90+% of the field is poloidal, and here it's 99% plus in the poloidal field. And then 16 sig, which is not only a well-studied solar analog, but also in our Kepler sample. It has been observed with this same technique, and despite an outrageous signal-to-noise ratio, no Zeeman signatures were detected in these stars. And keep in mind that the dipole component is the easiest component to pull out of this technique. It gets harder and harder as you move to smaller and smaller spatial scales. So if a dipole component were there, it would be the easiest thing to detect. So this is, again, we suggest circumstantial evidence that the dipole component of the field, or the largest scale components of the field, are disappearing across this transition. Okay, so how does this connect to the cycles, to the activity cycles that we see in other stars? I've been showing this diagram for a long time, since it first came out in 2008 in Erika Bonvitense's work. She was not the first to discover that there were these two different relationships between rotation period and cycle period. She was the first to present it in this way. And so basically, this is for the Mount Wilson sample of stars, updated with a few more recent detections. And if you look at all those stars where you have clearly detected, very clearly detected cycle periods and rotation periods, there's not just one relationship between those two things, there's two different relationships. And they call these the active branch and the inactive branch, okay? And the speculation is, these vertical dotted lines connect a single star that shows cycles on both branches simultaneously. So this suggests that these branches represent distinct dynamo mechanisms, maybe operating in different regions of the star, that can operate simultaneously, because some stars show cycles on both branches. But there's clearly a regime in which the active cycle branch is dominant, and then maybe it transitions in some way to the inactive branch becoming dominant. And that transition happens around the rotation period of the sun. What a coincidence. That was troubling at the time, but I think we now are in a position to understand this at a deeper level. So here's 18 SCO. Can you see this sort of shaded region? Well, there's this shaded region around the sun, a range of rotation periods where there are no detections of cycles in the Mount Wilson sample. Now, that's not because there are no stars in that range of rotation periods. There are. All of those stars show flat activity records. They don't cycle. And so the thing that makes the sun, with its 11-year cycle, an outlier in this representation is not that it shows an 11-year cycle, but that it shows a cycle at all. Most of the stars in that range of rotation periods just don't show cycles. And the Maunder minimum and grand minima-like events may be one indication that the sun's magnetic activity cycle is starting to sputter out, and it's eventually going to join the other stars in the Mount Wilson sample that just don't show cycles. The other piece of evidence here is that all of these stars over here at long rotation periods that show cycles are K-type stars. And there's a very good reason for that we now understand, that the G-type stars have stopped spinning down around the rotation period of the sun. And so they never make it to those long rotation periods until they become subgiants, and then they don't show regular Dynamo-like cycles. The only other thing I'll note is that over here where these dual cycles are common, the Mount Wilson survey classified many of these stars as chaotic variables. But we speculate that what appears to be chaotic variability is actually due to the fact that these secondary cycles on the inactive branch may be ubiquitous. All stars have them, and they get shorter and shorter over here at short rotation periods, and the seasonal data gaps between the Mount Wilson survey epochs didn't sample those short timescales properly, and so you get a chopping caused by these short cycles that looks like chaotic variability, but is actually dual magnetic cycles operating in the stars. Okay, the one last thing that I'd like to mention is looking forward, the successor to the Kepler mission, the TESS mission, will do essentially for the full sky, for brighter stars, what Kepler did for this one small patch of the summer Milky Way. And we will, a few years from now, have at least some form of asteroseismology for the whole Mount Wilson survey. And so we'll be able to characterize the ages and other properties of those stars at least a lot better than we currently can just a few years from now. So I'll just leave you with a few takeaway points. Summarizing the story, that we think a change in differential rotation at a Rossby number of 1 pushes stars across the Vaughan-Preston gap, rapidly decreases spot area, and then disrupts magnetic braking at this critical Rossby number of 2. And the evidence suggests that the sun is in this transition right now, and that we have to consider its 11-year activity cycle to be a special case of stellar dynamo theory. And maybe these other stars from the Mount Wilson survey will be better able to reproduce those cycle periods than we'll have better luck with them than we've had with the sun in the last decades. And we're hopeful that future Zeeman Doppler imaging maps, with a lot of the spectropolarimetric instruments coming online, additional constraints on differential rotation, clearly we need, and asteroseismology of the Mount Wilson sample from TESS will all be helpful to test this scenario moving forward. And here are the references for the 2 papers I mentioned if you want to read more about it. Thanks so much.